Welcome to the last session of the spring school today. This talk also serves by dual purpose also as theory colloquium. The speaker is Bruce Allen, who is director of the Max Planck Institute for Gravitational Physics in Gorleben near Potsdam, and he's gonna give an update on gravitational wave detection. Please.
Can you hear me? Yes, okay, good. By the way, our institute has two parts. One part is in Potsdam, near Berlin. I'm actually at the other half, which is the more experimentally oriented part, which is in Hanover, so about 250 kilometers away. Anyway, thank you very much for inviting me. So after about 50 years of development, we've made the first direct detections and observations of gravitational waves from the mergers of black holes. The picture behind me shows one of the two LIGO detectors. This is in Hanford, Washington. So I'm going to talk about what we've seen in our data so far and what it means. The basic physics of the observations is very simple, and so I'm going to show you the basic physics. Most of you are particle physicists, I think, by background or training. And so I wanted to start off with a quote from one of my physics heroes, Richard Feynman. One of the important things about these observations is that they let us test general relativity. The other useful thing is it gives us a way of observing the universe. There's a second reason I put this picture up here, which is that from having read Feynman's work and also having met him and talked to him once, I think he would have liked the physics, which I'm going to describe to you. It's very simple and very direct, and I think it would have appealed to him. So the thing I'm going to talk about the most was our first detection, which was announced on the 11th of February last year, almost exactly a year ago. This made the front cover of most US and European newspapers, and these are a couple that people here at Geneva might have been reading. This one says, "The universe has spoken." This one is, to me, somewhat more interesting and typical. Gravitational waves, the discovery that shows Einstein was right. Now, of course, in physics and science, you can never show that something was right. You can only show that it was wrong. So, of course, this doesn't show that Einstein was right, but it does show that one of the really important predictions seems very consistent with our observations. Okay, so here's an outline of my talk. I'm going to give you a very short introduction to gravitational waves. I'm going to talk about our first discovery, which is shown here on the cover of Physical Review Letters. And this was actually 4 days before we were going to begin our first observational run. We know that this was produced by the merger of two black holes, 29 and 36 solar masses. And I'm going to spend most of my time talking about these questions. What did we see? How can we be sure it's two black holes? What was going on behind the scenes, which you don't get in the papers? What other discoveries did we make during this first observing run? And I'll also tell you briefly something about the status of the second observing run. And if you want to learn more about this, read this paper. It's well written. And then there's a couple of other references in here, a PRX, which summarizes the first observing run. And this article in Annales der Physik gives the simple physical argument I'm going to show you for how we conclude that this was two black holes. Just briefly, I'll just tell you a little bit about myself. I've worked on the data analysis problem for gravitational waves for a couple of decades now. There's about 40 people in my group at the AEI who also work on this. We, for example, run some large computing systems that do analysis of LIGO data. Also run a volunteer distributed computing project to look for other types of signals. So I've been involved in the data analysis side of this. As I said, the central reference for what I'm going to talk about is this discovery paper from a year ago in PRL. This paper is carefully written. a large group of people argued over every word in every sentence in this paper. So it's a well-written paper, and anybody here should be able to read this paper. I'm just curious, who here has read the paper?
PRL?
This PRL? Okay, all right. In fact, this paper has already accumulated more than 1,500 references. It's getting more than 100 a month. Okay. So let me show you one slide about gravitational waves. Now, there's a lot of smart, well-trained people here. And for particle physicists, gravity is a spin-to massless field. The first prediction of gravitational waves is in this paper from June 1916. This is about half a year after the publication of Einstein's theory of general relativity. And this is perturbative integration of the field equations of gravity. And you can see here, he says it then follows that the gravitational field spreads out at the speed of light in connection with these general solutions will oh gosh, that's hard to translate. Okay, we will investigate these solutions of Einstein's equations and the systems that give rise to them. So anyway, there's really three key things you'll need to know from my talk. One is that gravitational waves propagate at the speed of light. The second is that for velocities of the sources that are slow compared to the speed of light, the dominant form of radiation is quadrupole radiation. I'll explain why dipole radiation is absent in these systems. And third thing, in this regime where the velocities are slow, the luminosity of a source is given by this equation. So this is Newton's constant divided by the fifth power of the speed of light. And then what you have here is the square of the third time derivative of the mass quadrupole. So QAB here is the integral of the of the mass density rho times XA XB with the trace removed. By the way, Einstein, in this paper, made some estimates of what this luminosity would be. And the problem is that this factor of g over c to the fifth is so small that he wrote that probably this radiation had no practical consequences or no meaningful consequences. And I'm happy that that's actually wrong, although, of course, it took 100 years before it became wrong. Okay, so let me just tell you briefly a little bit also about the instruments. So this LIGO, this word here, is actually an acronym. It stands for Laser Interferometer Gravitational Observatory. This shows the other LIGO detector. There's two of them. The one that I showed you on my cover slide was the one in Hanford, Washington State. This is the one in Livingston, Louisiana. It's 3,000 kilometers away, which is 10 light seconds of travel time. So a gravitational wave, since it goes at the speed of light, has to arrive within plus or minus 10 milliseconds at the two instruments. And what you see from the outside is you see here a concrete beam tube cover. This arm is 4 kilometers long. There's another arm here that's 4 kilometers long. The detectors are actually oriented oppositely, but as close to parallel as you can make them, given that the surface of the Earth is curved. So they are sensitive to the same polarization of gravitational waves. And the way that these instruments work, I'll explain to you in the next slide. But they're sensitive to gravitational waves in the audio band. So that is gravitational waves with frequencies that are tens of hertz up to a couple of kilohertz. And the measure of sensitivity, as you'll see, the way these instruments work is they have mirrors that hang 4 kilometers apart in these tubes. And we sense small displacements of these mirrors. And the sensitivity of the instrument is expressed in terms of strain, which is the fractional change in the length of of one of the arms. And this plot shows a power spectrum of the noise in the two instruments. So one instrument is red and the other instrument is blue here. And you can see this covers a frequency band here, which is audio band, so 20 cycles a second up to 2,000 cycles a second. And the vertical axis here shows the spectral density of noise in this quantity, fractional change in length. And so, for example, at the minimum here, which is, let's say, from 100 to perhaps 400 hertz, this is about 10 to the minus 23 per root hertz. So, for example, if you filtered the data to extract, let's say, a 100 hertz wide band here, so 100 to 200 hertz, then the root mean square noise in that bandwidth would be the square root of the bandwidth here, which would be 100 hertz times this number, 10 to the minus 23 per root hertz. So RMS fluctuations in that band of about 10 to the minus 22. And that's a remarkable number if you think about it. We're measuring fluctuations that are 10 to the minus 22 of a 4-kilometer distance. So, for example, I was at a talk earlier this year in Vancouver where a scientist was talking very proudly about the fact that using reflectors on the moon, you can measure the distance to the moon to a millimeter accuracy, which, isn't bad, right? It's, the moon is a quarter of a light second away. And so that's about a part in 10 to the 11. It's 10 to the 10 centimeters away. And I said, well, okay, part in 10 to the 11, that's really not bad. But if you could measure the distance to the nearest star with 10 to the minus 22 precision, that would be 40 microns. So just to give you an idea of the scale here. Okay. How do these instruments work? So here's a movie to illustrate it. They consist of a light source, that's a laser, that illuminates a beam splitter. The beam splitter is hanging. The light travels down the two 4-kilometer arms and bounces off mirrors, which are also hanging. They're suspended. And then the light recombines, and you can see here that it's out of phase and cancels. So there's no light coming through this port. If a gravitational wave comes by, what happens is it distorts the space-time geometry and changes effectively the length along the two arms, and then some light leaks through. So that's the basic principle of operation. Okay, so let me talk about our first observation, our first detection. So we call the event GW for gravitational wave. 15 is the year, 9 is the month, and 14 is the day. And this took place during the preparatory phase before our first science run was scheduled to begin. It was scheduled to begin 4 days later. And in fact, what we've done in the last month before that is a process of final tuning and shakedown, which includes, for example, calibrating the instrument by putting known signals into it. What we do is we actually move the test masses and then see what comes out. And some of that motion is sinusoidal things for calibration. Other motions are simulated signals to see if our whole data analysis chain is working. And the first observing was scheduled to start on the 18th of September. At the time this event happened, the Virgo instrument in Kashina was not operating. GEO 600 that's operated by our institute had lost lock about 10 minutes before. It wouldn't have seen this event anyway because this was a low-frequency event, and that instrument's not sensitive at low frequencies. So when the event actually happened, it was the small hours of the morning in the United States. It was 3 o'clock at LIGO Hanford. It was 5 o'clock in Livingston, Louisiana. In Germany, though, it was just before lunchtime. And the first two people to be aware of this signal were actually both postdocs in my group. Marco Drago works on a real-time analysis pipeline called coherent wave burst. And in fact, he was in the process of moving that pipeline, which is running on some computers at Caltech, to running on computers at the AEI, which was what had been planned for the science run, when this event happened. He got an alert and looked at it. Now, it might be interesting for you to realize that at that point, the event database of alerts already had about 1,000 alerts in it, because we'd been generating alerts by doing testing. and noise events generate alerts as well. But Marco looked at this and was surprised by what he saw. It looked like a really nice signal. And he checked some of the logs and other places where we record tests, and there was nothing recorded there. So after a few minutes, he walked down the hall to talk to Andy, who's co-chair of the detector characterization group. He studies glitches and sources of noise in the instrument. And Andy did some more extensive checks. Eventually, the two of them actually called the LIGO operators on the site, who told them that there's no testing going on right now. Everybody's gone home. And finally, after about an hour, Marco sent an email to the collaboration. And the last sentence of his email says, "Could somebody please confirm that this is not a test signal?" And that then provoked a flurry of emails, hundreds, and then subsequently, I think, thousands. And the decision to lock down the sites, meaning stop making changes, no more tuning, no more modifications. Because if we wanted to establish that the event was real, that it wasn't just a noise fluctuation, we needed to have statistical properties that weren't changing anymore. We needed to be able to characterize the noise, so we couldn't change the instrument anymore. And that decision was made rather rapidly, and our first science run began a few days earlier than planned. So this is what Marco and Andy saw when they looked at this data. So here you're looking at about a quarter of a second of time, and this is the strain, the fractional length of change in one of the arms at the two sites. And here I've shifted, the signal arrived 7 milliseconds earlier at Livingston, so I've shifted it 7 milliseconds in time. And so what you see here, and this is bandpass filtered up to about 350 hertz, and also has some calibration lines removed. And so what you see here, first of all, this earlier time is fluctuations. And the scale here, this is 10 to the minus 21. So these fluctuations have an RMS, which is of order 10 to the minus 22, which you'll remember from the noise power spectrum is exactly what you'd expect for the RMS fluctuations in a 100 hertz wide band. Okay, and then you can see rising out of this noise here is this pattern with increasing amplitude and frequency, which reaches a peak and then dies away. Now, that signal lasts a quarter of a second. But for somebody who's worked on this for a few years, it takes less than a quarter of a second to say, that's two black holes. And I want to show you the logic behind that, which is very simple and very direct. And that's the main physics content of my talk, is what's going to come in the next 10 or 15 minutes. So what does it mean when you see something oscillating back and forth? Well, normally, if you perturb a system out of equilibrium, then it oscillates and eventually damps away and comes back to that. So you say to yourself, maybe we're seeing something like this. But of course, this kind of oscillation tends to have a fixed frequency and a decreasing amplitude. Whereas the signal that you saw has an increasing frequency and increasing amplitude. It doesn't look like that. Now, there is one system we know which does produce that kind of signal, and that's orbital motion. If two objects orbit each other, because of the quadrupole formula, what I showed you earlier, that has a changing quadrupole moment, it emits gravitational waves, that carries away binding energy from the system. And so what happens is the two objects move closer together, and when they move closer together, they orbit faster. It's unstable. This makes them emit gravitational waves with larger luminosity, and they lose energy more quickly and fall together. And so that produces a system with increasing orbital frequency and increasing gravitational wave luminosity. So it produces a signal like the one that we saw. Now I'm going to show you a very simple calculation of that, because it's easy to do. And this is something which I think somebody like Feynman looking at this would have done rather quickly. So I want to just do an analysis for you, the very simplest one. We take two objects of equal mass moving on a circular orbit at distance r, and just analyze the thing I just told you in words. So if you just apply F equals ma to this, the gravitational force of attraction has got to equal the centrifugal force pulling the two objects apart. Since I've got the distance being r, the radius is r over 2. So this is just mass times omega squared times the radius. And if you just put r on one side and omega on the other, this leads immediately to one of Kepler's laws. I can never remember which one that is. Does anybody remember? The third one, I think. I'm not sure. Okay. Is it the third law? Thank you. Okay. This says that the square of the orbital time is proportional to the cube of the orbital radius, or semi-major axis, or something like that. Okay. Anyway, that's one of Kepler's laws. Okay. Now, what's the mechanical energy of the system? Let's just sum it up. You've got the kinetic energy of the first mass, that's 1/2 mv squared, plus the kinetic energy of the second mass, so here's another 1/2 mv squared. And then you've got the gravitational binding energy, which is gm squared over r. So anyway, you add these three things up, you replace omega with this relationship here in that, and you derive the virial theorem, that the total mechanical energy here is 1/2 of the potential energy. Okay. So if you want, you can replace the mechanical energy here. You can rewrite this in terms of omega. Since this goes like 1 over r, that means it goes like omega to the 2/3 from this relationship, since r to the minus 3 goes like omega squared. So anyway, so the mechanical energy is given in that expression in terms of the orbital angular frequency omega. Okay. Now, I commented earlier that in general relativity there's no dipole radiation. It's worth thinking about why that is for just a minute. So suppose this was electromagnetism. You could write down the dipole moment. It would be the sum of the charges times the vector away from the origin. So let's suppose you try and do the same thing here. Suppose you try and write down the mass dipole moment. So it's the sum of the masses times the vector positions. Well, if you did that, and then you took a derivative of this, this would be the masses times the velocities, which of course is just the total momentum. Now, the thing that enters in the dipole formula in electromagnetism is the second time derivative of the dipole moment. So take one more derivative. Here's a second derivative. But remember, the momentum of a closed system is conserved. So the second derivative just gives 0. And this is, roughly speaking, why there is, at least at low order and velocity, no dipole gravitational radiation. So in the system like this, you can see very clearly there's no dipole moment. And so maybe not so surprising that quadrupole radiation is what dominates. Okay. So now let's go back to the formula. I told you it was one of the 3 things you needed to know about gravitational radiation for my talk. And here it is. Here's g over c to the 5th, and then the square of the third time derivative of the quadrupole moment. Now let's compute that. Okay, well, the quadrupole moment, that's a mass times a distance squared. So in this system, it must be the mass times the radius squared. And indeed, you can see in computing this, I've got g over c to the 5th here, and here's the mass times the radius squared, and I've squared it again. And I've actually done the math to figure out there's a factor of 8 in front there. Okay. Now, what about the 3 time derivatives? Well, of course, in Newtonian mechanics, this thing just orbits periodically, angular frequency omega. So 3 time derivatives gives you an omega cubed. And of course, you square that. So here's omega to the 6th. So here's what Einstein's formula for quadrupole radiation tells you about the luminosity of this system. And so now if you replace r to the 4th here by the appropriate power of omega, and you combine the omegas, you notice that the luminosity goes like a rather high power of the angular frequency. It's omega to the 10/3. All right. So now, let's do the next step. So far, our analysis has just used Newton's laws of motion, and then we pulled this quadrupole formula out of a hat. But now let's put the 2 things together. Suppose that the gravitational radiation is not large. Suppose that the amount of energy that's pulled out of the system per orbit is much smaller than the total energy. Then the effect on the system is going to be adiabatic. And we can analyze that very simply. in a case like I just described, the luminosity, the gravitational wave luminosity, is just loss of mechanical energy. And we have a formula here for the total mechanical energy. It goes like omega to the 2/3. So if the mechanical energy is changing slowly because of gravitational wave luminosity pulling energy out of this system, then the time derivative of the mechanical energy is the time derivative of omega to the 2/3. That's 2/3 omega to the minus 1/3 times omega dot. So here's the rate of change of mechanical energy, and you notice now it's going to change the angular frequency. And now we can equate this quantity, omega to the minus 1/3 times omega dot, with this, omega to the 10/3. And if you do that, you end up with a first-order differential equation for the rate at which the frequency will evolve due to the back reaction. As the gravitational waves suck energy out of the system, the angular frequency goes up. And you notice, by the way, that the angular frequency, the rate of change, is a high power of omega. It's almost omega to the 4th. So as the frequency goes up, it goes up faster and faster. And that's the kind of thing that we observed in our data. Does anybody want to ask me any questions about this? Okay. When I was a kid, I sometimes used to daydream in school about, what would happen if I was dumped on a desert island, or shot back to the 18th century with no knowledge other than what I had in my head. What could I do? And anyway, this is a calculation which I think it's one of those things that sort of anybody should be able to do on the back of the envelope, just to convince themselves about how a system like this behaves. Okay, now because this is quadrupole radiation, it means that each orbit of the two objects around each other makes two complete cycles of gravitational waves. You can kind of see that in this cartoon here if you follow the orbiting objects outwards. Also follows from symmetry in the case where the two masses are equal. So let's go back to our data again and ask what we're looking at. So what you're seeing here is you're seeing orbits. There's an orbit. These two cycles are another orbit. Here's another orbit. Here's another orbit. And then something happens there. The two objects collide together, and this kind of simple description that I've been giving you breaks down. Well, the formula I just derived for you, the rate at which the frequency evolves, depended on the masses of the system. And so here I've written down for you the formula in the case where the two masses are not equal. So masses m1 and m2. And remember the formula I had for frequency evolution. I think I'll go back a couple of slides here. In this formula for frequency evolution, omega dot goes like omega to the 11/3. So that means that omega dot times omega to the minus 11/3 is a constant, which is related to the mass. So here, you see the same thing. I've now called it frequency. This is gravitational wave frequency now, not orbital frequency, so a factor of 2 difference. So the frequency derivative times frequency to the minus 11/3 is related to a combination of the masses. And that combination of the masses is called the Chirp mass. And the beautiful thing about this is you can look at our data. So here's our data plotted. Here's 150 milliseconds, so almost a quarter of a second. And here's frequency going from 32 up to 512 hertz. And here you can see our signal sweeping up in frequency. So we can pick some different points on this curve, like that one, and say, okay, what's the frequency and the frequency derivative at that point, or at this point, or at that one, and stick it into this formula. And from that, we find out the characteristic mass of the system. In other words, the rate at which the frequency is evolving tells us how much do these objects weigh. If they were light objects, the frequency would evolve slowly. If they're heavy, the frequency evolves quickly. If you stick the observed values of frequency and frequency derivative from here into that formula, you learn right away that this combination of masses is about 30 times the mass of the sun. So we find out how heavy the objects are immediately from the observed data. Now, this actually leads immediately to the conclusion that this must be two black holes. And let me explain the logic. So, the fact that the Chirp mass, this combination of masses is 30 solar masses, well, if the two objects were both the same mass, then each one would have to be about 35 solar masses. And if an object of 35 solar masses has a Schwarzschild radius of about 100 kilometers. So the sum of the two Schwarzschild radii in that case would be about 200 kilometers. Now, if you make the masses unequal, what happens is the sum of the Schwarzschild radius has to be larger. So we can tell already from the mass that the sum of the Schwarzschild radii of the two objects is more than 200 kilometers. Now, the other thing to look at is look at our signal. Remember, it chirps up in frequency, just like we were describing in that calculation, until it reaches a peak here. And then suddenly something happens. The two objects touch or merge or interact somehow, and this simple evolution ends. Well, the frequency here at this peak is about 150 hertz in gravitational waves. You can see that, by the way, just by measuring, for example, the time between this and the next cycle. And that's half a cycle. So that means that the objects are orbiting each other about 75 times a second. Now you can go back to your Newtonian calculation and say, how far apart do two objects have to be that weigh 35 solar masses in order to orbit 75 times a second? And the answer comes back 350 kilometers. So now ask yourself, what could these objects be? Could these be ordinary stars? I mean, ordinary stars, at least heavy ones, could weigh up to 30 solar masses, so that's possible. But the trouble is that ordinary stars are much too big. They're 1 million kilometers in size. They couldn't get 300 kilometers apart without having merged. Maybe they could be white dwarf stars. Those are smaller. But white dwarf stars are 10,000 kilometers in size. Again, they would have touched before the gravitational wave frequency even got up to 1 hertz. The only objects we know of that are so compact and so heavy that they could still be orbiting at separations of a few hundred kilometers and weigh 30 solar masses are black holes. There's nothing else that we know of. Or at least I should say there's nothing else that we've observed in the universe. By the way, you might ask yourself, maybe one of the objects is a neutron star. Those weigh 3 or 4 solar masses. The trouble is that in order to get the Chirp mass of 30 solar masses, if one object was a neutron star weighing 3 or 4 solar masses, the other object would have to weigh something like 600 solar masses. And again, that's too big. You can't have one object orbit the other one quickly enough to produce the waves that we saw. So that's also ruled out. So, conclusion is that these must be black holes. And the logic is just very simple, as I explained. This is a numerical simulation done by Alessandro Bonanno and postdocs at the AEI. What you're going to see here is the smaller and larger black hole, and on the bottom here is the waveform. And I'm going to show you only the last half dozen orbits. By the way, in the calculation I just did, the two objects had a Chirp mass of 30 solar masses and therefore individual masses of, say, 35 and 35. You notice those are somewhat larger than what I reported in one of my earlier slides where I said 29 and 36. And that's because the calculation I just did is in the detector frame. It's using the data at our detector. Whereas we know these objects had a redshift of about 0.1. And so they had somewhat lower mass at the source, but then the waves got stretched out by the expansion of the universe and make it look like it's higher mass at the detector. It's about 10% different. Okay, here's the simulation. The two objects orbit. As they orbit, the orbital frequency, the amplitude goes up, then they merge together, and you end up with a single Kerr black hole at the end.
So it's simulation or just schematic?
This is a numerical simulation. This is solving Einstein's equations on a computer. And by the way, there's several other simulations like that if you want. You can look on the web, done by different groups. Just for fun, I just want to point out that, for example, if you also want to know the distance to this object, you can also get that by crude back-of-the-envelope calculation. And it goes like this. We know from the data that the maximum strain at our instrument was about 10 to the minus 21. That was the strain at the peak of the gravitational wave. Now, if we were a factor of 10 closer to that system, because the strain falls off like 1 over the distance, just like the electric field does, for example, in electromagnetic radiation, then the maximum strain would have been 10 to the minus 20. If we were another factor of 10 closer, then the maximum would have been 10 to the minus 19. We continue that argument up until you get to a horizon scale away from this system, and then the strain would have been about 0.1. So that means that the distance to the source must be about 20 orders of magnitude larger than the Schwarzschild radius, which is a couple of hundred kilometers. So put in the numbers, and you'll see that we were of order 1 billion light years away from that object when it merged. So in fact, we believe that mergers like this of two black holes take place in our Hubble radius, so in the observable part of our universe, perhaps once every 15 minutes. We don't see them all because our instruments aren't sensitive enough. We only see the ones that are close enough that they produce a large strain in the instrument. So I explained to you how this was first seen, and in fact, I saw that signal about an hour after Andy and Marco first looked at it, and I still remember my first reaction was, that's too good. That's an injection test. Somebody's put that signal in and they forgot to log it in the logbook. And in fact, many of us were quite consumed by this for a number of weeks. So the question is, was this thing real, or was this an artifact of the detector or of human activity? So the instruments had been operating normally since about the 12th of September. The initial LIGO, the advanced LIGO instrument, could see things like this at about 6 times the distance as the initial LIGO instrument, which means a volume that's about 200 times greater. So 2 days of observation with the new instrument was the equivalent of 400 days of observation with the old one. So not surprising maybe that we didn't see this in the initial LIGO. At the sites, Stefan Ballmer and Evan Hall were the last people in Hanford. They left around midnight, a couple of hours before the event. In Livingston, the last people on site were Robert Schofield and Anna Marie Effler. They actually left about half an hour before this event happened. And this is a bit of good luck. They were actually planning to do one more set of tests called the bump test, where they drive a car over the speed bumps in the parking lot to see what the effect is on the instrument. It doesn't sound very scientific, but they do this with a GPS synchronized clock in their hand because they try and drive over the speed bump at some exactly delineated moments. And their GPS clock had lost synchronization, and they decided that was a good sign and they should go home and get some sleep. Otherwise, they might have just knocked the instrument out of lock, and we never would have seen this. This signal doesn't look anything like the instrumental glitches or artifacts that we normally see. We could also ask whether this was due to some external disturbance. Well, we monitor things like the radio background, the acoustic background, and so on. And we also measure the transfer function of those things to the instrument. So, for example, we create a magnetic field, and we see what effect does that have on the gravitational wave signal. And that gives us a transfer function. And then we can actually multiply the observed magnetic field by that transfer function, trying to estimate what effective gravitational wave signal would that have produced. We can't explain more than about 6% of the amplitude in this way. And finally, the thing I was most worried about was that this was an accident or malicious, that we'd actually created this signal ourselves. In the end, a group at MIT ruled that out because the control loop of the instrument is recorded at a number of points around the control loop. And what they did is they reconstructed what was happening inside the control loop of the instrument. And you can see that during this event, what's pushing the test mass is not something from inside. It's something from outside. So, in fact, we're even able to rule out the malicious case here. Now, there's another possibility, too. If you seat a monkey down at a typewriter and you wait a while, eventually the monkey will type the word hello. And you wait longer and they'll type hello, Bruce. And in a similar way, if you just look at the effects of instrumental noise, eventually the instrumental noise in one of the instruments will produce one cycle that looks exactly like our signal. And if you wait longer, the noise in the instrument will eventually produce 2 cycles that look exactly like our signal, just Gaussian fluctuations. Wait still longer, and eventually, the noise will make a waveform that looks exactly like what we observed at one of the instruments. If you wait still longer, you'll get that waveform at the other instrument as well. And if you wait even longer, you'll get the same thing within plus or minus 10 milliseconds. So you have to ask yourself the question, how long would you have to wait before Gaussian noise in the 2 instruments would give you coincident signals that look like one of our models? And we eventually answer that question. I guess in the discussion I can show more about this, but if you're interested. But the conclusion is we'd have to wait much longer than 200,000 years. We weren't actually able to determine how long you'd have to wait. It's probably more like the Hubble time, the age of the universe. We were just able to put a bound that was long enough to make this a gold-plated 5 sigma equivalent in one-sided Gaussian noise event. So convincing enough to publish. To learn more about the system, we model the parameters. And the way we do that is for particular parameters like the masses and the distance, we generate a waveform using analytic and numerical models. We subtract that from the data, and then we ask, is what's left over consistent with noise in the instrument, just with pure noise? And we do this many, many times with Markov chain Monte Carlo methods and so on. And eventually we determine the parameters of the system. Now these parameters are in the source frame, not in the detector frame before. So we have the larger mass black hole being about 36 solar masses, the smaller one being 29. Final black hole mass being about 62 solar masses. The redshift is about 0.1, putting the system at about 400 megaparsecs. To me, one of the most amazing things about this system is the total amount of energy that was radiated. So those last couple cycles of the waveform are the ones with peak luminosity. And the system, you notice, goes from a total of 65 solar masses before the merger to 62 after. It lost 3 solar masses of energy. Now, for example, our sun is going to burn for billions of years, and it converts maybe 1% of its mass into radiant energy. So this system, converted 100 times that amount of energy in some milliseconds. So briefly, it was brighter than the sum of all the electromagnetic emission from all the stars in the universe. And just to put this into sort of regular units, if I take my cell phone here, this is 500 milliwatts when it's transmitting, half a watt. And I hold it at arm's length, about a meter away, right? The sphere around that, it's a meter in radius, it's got 10 to the 4 square centimeters in it. So this thing is a few microwatts per square centimeter. So this black hole event was also, by our instrument, a flux of around a microwatt per square centimeter. The difference, of course, is my cell phone is 1 meter away. This system was 1 billion light years away. So you could say that our instruments are really crappy, right? They require a signal so strong that, for example, in radio astronomy, the typical pulsar signals are 12 or 15 orders of magnitude weaker than this. Put this in X-ray astronomer units, and it's 10 to the 12 millicrab. Enormous. Okay, I think I'm not going to talk about what 3 solar masses means. Maybe just a quick anecdote. I took my younger son to see the latest Star Wars movie around the time that we announced this discovery. And he was very unimpressed by the whole thing. I mean, 3 solar masses, energy. But anyway, during the latest Star Wars movie, the Death Star comes back. And the Death Star is this horrible war machine which can evaporate planets. And so I was sitting in this not very good movie thinking, how much energy does it take to evaporate the Earth? And if you work it out, you realize that 3 solar masses is enough energy to evaporate our planet and every other planet in the galaxy. You can evaporate 10 to the 12 planets with that. So it's really a lot of energy. I told my son that, and then he was impressed. Okay, I'm going to wind up my talk pretty soon, but We did follow-ups, not we, but our astronomical partners, basically over a broad range of energies, including gamma rays, X-rays, optical, and radio. There is one report of a gamma ray burst 0.4 of a second after, which I'm very skeptical about. So I think executive summary is that there was no electromagnetic emission, which is what you'd expect from the merger of two black holes. Later in the observing run, we saw, so this is the signal that we saw, which we've talked about at length. Later, the day after Christmas, we saw a somewhat weaker signal noise of 13. It didn't stick out above the noise, but if it had stuck out above the noise in a visible way, this is what you would have seen. It's a lower mass system, so the frequency evolves more slowly. And this is about 30 solar masses, so lighter than the other system. We also saw a system where the false alarm rate is 1 in a few years. It could have been a noise artifact. I think it's a real signal, but we didn't claim that as a detection because it doesn't exceed 5 sigma in terms of its equivalent false alarm rate. I'll just make a brief comment here for the experts. One of the things I was excited about by here with this detection was the idea of testing Stephen Hawking's area theorem. By the way, Hawking's area theorem, which says that the horizon area of black holes always goes up in any interaction, sort of the equivalent of the second law of thermodynamics, is interesting to read. It's from 1971, and the first sentence says, Weber has recently reported coinciding measurements of short bursts of gravitational radiation at a frequency of 1600 hertz, occurring at a rate of 1 per day. It seems likely that these were caused by collapsed objects, and then the question is, how much energy could you release from black hole mergers? So in fact, the rationale behind the area theorem was exactly trying to explain reports that turned out to be false about gravitational waves. Anyhow, Hawking's theorem just says that the final area is greater than the sum of the initial areas. You have to multiply by a factor of 8 pi here to get the areas. So here's the final black hole mass and final black hole spin and the initial mass and spin. If you plug in the masses and spins from the earlier transparency where I gave you the parameters, you'll see that the area theorem is satisfied. It's very, very nice. But it turns out that actually we're not testing the area theorem in nature. And the reason why is because if you look at our waveform, the part of the waveform after the merger, that's this part here, has almost no signal to noise left compared to the earlier part. So the way that we're getting our final mass and final spin is not directly from the data, which would let us test the area theorem. Instead, they're coming from numerical relativity, where we put in the initial conditions here and then numerically solve Einstein's equations to find the final mass and the final spin. So if we had found a violation of the area theorem, it just would have meant that the people numerically solving Einstein's equations had made a mistake. Because if you solve Einstein's equations correctly, the area theorem will be obeyed. So we can't test nature yet. Now, we might find another system in the next years, which is, let's say, a factor of 2 closer to us, and we have an instrument that's a factor of 3 more sensitive, and then we will get enough signal to noise in this region to test the area theorem. Okay, well, our second observing run began in November last year. It's turned out to be more difficult to increase the sensitivity as we had hoped. I'm expecting that we're going to record at least a handful of events, maybe as many as 10 in this next run. And we're hoping also that Virgo will join this run as well, providing additional pointing and polarization information. A week or two ago, the collaboration agreed on a statement about the status of our current run, and I'll just put it up here. Say that so far we've identified 2 event candidates, and we are investigating these thoroughly. So here's a brief list of things I didn't talk about. One of my very first slides was a picture of Feynman and a quote from him. So we have compared the waveforms that we observe with the predictions of general relativity. They're completely consistent. And this is remarkable because we're testing general relativity now in a regime where the objects are relativistic. They're moving at 3/4 the speed of light. So I guess a true particle physicist would say that's not relativistic. But nevertheless, it's much more relativistic than previous tests of general relativity. And the gravitational fields are strong. That is to say, near the horizon, the field strength is of order 1. And so these objects are really testing the strong field theory. There's some astrophysical implications in order to form such large black holes. The metallicity during the star formation period could not have been too big, or else those stars would have evaporated too quickly and not left behind such massive objects. We have a very broad limit on the event rate. This will get much more precise with additional observations over the next few years. For each system that we observe, like the one I showed you, there's 1,000 such systems 10 times as far away, which don't stick out of the noise, but they produce a correlated background of noise between the two instruments, which eventually I think we'll be able to detect. And this will tell us something about the mass distribution and the formation history of these objects at cosmological distances. There are, of course, many other potential LIGO sources, which I haven't talked about. And there are current and future instruments and methods to detect gravitational waves in other frequency bands. So the next few years are going to be a golden age for gravitational wave astronomy. I think by the time that LIGO reaches its design sensitivity in the next 2 to 3 years, we'll be able to observe over a period of a year about 100 events like this. So, for example, we'll know the mass and spin distributions of these types of objects. We'll also hopefully observe one object close enough and with a sensitive enough instrument that, for example, we'll be able to test the area theorem directly from the observations. So here's the conclusions. We can detect gravitational waves directly. We can observe the amplitude and the phase of the waves. And as you've seen, there's a lot of information there. We've established the existence of stellar mass black hole binaries. And if you think about it, there's no other way to detect these things because, after all, they're black holes. They don't emit light or radio waves or X-rays. So we can only find these things through gravitational waves. We're going to enter a golden age where we're going to go from the 2 detections I've talked about up to 10, up to 100. And I think that we're very likely to find other sources of gravitational waves, for example, merging neutron stars or neutron stars falling into black holes, or continuous wave emission from bumpy spinning neutron stars, or perhaps something unexpected, maybe bursts from cosmic strings or something like that. So thank you very much, and I'd be happy to answer questions.
Thank you very much. There's one question here.
Are there any chances to see an event from the local cluster?
You know, the local cluster, you're talking sort of 40 megaparsecs distance. Yeah, you'd have to wait a long time. I mean, we expect that, for example, a neutron star merger should take place in that volume maybe once every 200 years, 100 years. The binary black holes, you have to wait, I mean, a long time. Yeah.
I have a second question. After the recent developments in the United States, have you reconsidered the possibility that the events were fed by Russian hackers?
Yes. I'll tell you the degree that we went to. So, for example, the racks that contain the control systems, they were locked. They were locked and sealed on the day that this event was detected. And then they were unlocked by a group of people at the end of our observing run who hunted through them to see if somebody had plugged an iPod Nano in there, which had been programmed somehow. We figured there's maybe a half a dozen people in our collaboration who were smart enough and skilled enough to actually produce such a fake signal. So we actually tracked the movements of all of those people to find out where they were at the time of the event. But it's real. Yeah.
Other questions? or comments here?
When you say that you expect to see about 10 events this year and 100 events next one, where did you get those bands from? I guess it's astrophysical data, but what is exactly the...
No, it's nothing to do with astrophysics. It just has to do with the reach of the instruments. So the noise curve that I showed you for O1, remember this curve that showed the noise as a function of frequency? That's less sensitive than the design sense of the instrument by about a factor of 3. Meaning that as we make the instrument better, as we get to design sensitivity, we'll be able to see about 3 times as far.
Yeah, for sure.
And 3 times as far is 27 times the volume. So roughly speaking, if we see 2 events in 4 months, then with the final design sensitivity...
Everything is an extrapolation from your events.
Exactly.
There's no external input of
Correct.
How many binaries you expect to see in the universe from all the sources, right?
Correct. I'm just giving you a very crude order of magnitude estimate. Okay, that's just my personal estimate based on extrapolation.
Okay.
Further questions? Comments? Yeah.
Concerning the current status, so you said there are 2 candidate events. Are these all black holes? Is there anything for neutron star?
I'm not allowed to tell you anything else about them. Our collaboration does not want to release information except in the form of publications and statements like the one I read you, so I'm sorry.
Other questions or comments? Here.
If you kept the instrument exactly the same, how long before you would see another signal of the same quality?
Oh, that's a good question. So our very first detection was surprisingly strong. Who asked the question? Okay. Was surprisingly strong. So it had a matched filter signal noise of 24. So what that means, it means if that event had actually been twice as far away, we still would have seen it strongly enough to claim that as a gold-plated detection. So you ask yourself, how likely is that? Well, if there's an observable volume that the instrument can see, then, and we were a factor of 2 closer than that, then it means that we were in 1/8 of the volume. So our first event was almost like we won a bet, where the odds against us were 8-1. There's 7 chances out of 8 that it would be not in the 1/8 of the volume closest to the instrument, and 7/8 probability that it's in the other part. So roughly speaking, 1 out of every 8 events should be about that strong. And so that's one reason why, by the end evolution of this instrument, when we see 100 events, one of those should be another factor of 2 closer. And if the instrument is 3 times as sensitive, we'll get something like 6 times the signal to noise. So instead of having a signal noise of 24, it'll have a signal noise of 150. And even the post-merger part will be sort of clearly enough visible in the data that, for example, we can actually figure out the final mass and the final spin of the black hole without using any of the data from the earlier part. That's the sort of logic. Again, it's just scaling and extrapolation.
Yeah.
How can you place this event in a map of the
Yeah, it's a good question. So let me go back to the relevant slide here, and then I've got another slide I can show you as well. So I didn't talk about it, but down here is a map showing the region on the sky where the source was most likely located. It was sort of in this red region here. This is a few hundred square degrees. Now, how do we know that? Well, because we have 2 instruments, we can do a form of triangulation. Who asked the question? Okay. So here's instrument number 1, and here's instrument number 2. If the signal arrived at the same time at both instruments, then we'd know that it came from a circle equidistant. Now, because it came 7 milliseconds earlier at this instrument, we can now shift imagine taking a piece of string, stretching it out, a shorter piece of string, 7 milliseconds shorter, stretching it out, and then making a circle like that. So our source must lie from somewhere on that circle. That's the circle where the time delay to one instrument is 7 milliseconds different. So now if you look at this picture, you can see the circle. The circle is here. But now you say, this is strange. I don't see a whole circle here. I just see a little piece of it. Why is that? Well, here's the thing. Our instrument has L-shaped arms, and it's most sensitive to sources that are directly overhead or directly underneath. So if you draw that circle on the sky, you'll find that most of that circle doesn't lie in the region directly above or below. So Bayesian inference then says, okay, the most likely place for that source to be is on that circle with the right time delay and where it would have made a strong signal in the instrument. So that region in the sky comes from the relative timing, the fact that the signal arrived 7 milliseconds early at Livingston, plus the fact that our instrument is much more sensitive to a source that's directly overhead or underneath. And if we want better timing information, let me just drop out of I'll show you one of my backup slides here. I'm pretty sure I've got one. Yeah, so eventually we'll have a network of many detectors, and this will then give us, sky pointings, which are just a few degrees in size.
Further questions? Well, you.
There's many questions we have about the structure of the black hole horizons.
Mm-hmm.
Recently, there's been a paper called Echoes from the Abyss,
Mm-hmm.
which assumes that there is some structure and then gravitational waves could get trapped between the structure at the horizon and the angular barrier.
Yeah.
And then these could go through the barrier and you would measure echoes of these gravitational waves.
Yeah.
Currently, I think the signal is not strong enough to actually measure this, but could you maybe comment on future possibilities?
Let me just see if I've got something in a different time. I was going to show a slide about this if I could find one, but actually I don't think I've got it here. I've got it somewhere else. Okay. So the idea is that there may be signs, for example, of a firewall at the horizon or outside the horizon that are visible. So the idea is that the black hole system could produce echoes, and the way this would happen is the following. For example, the waves that are being produced, of course, they come out to infinity, but of course those waves also travel inwards. So the idea is that if you put some funny boundary condition, let's say at a few Planck lengths outside the horizon, then that might be reflective. It might actually bounce some of that signal back in. Now, you wouldn't see the inspiral part because that's too early. That's before the black hole forms. But you would see, for example, the ring down part of the waveform from the end. So some of that might go in, let's say, bounce off this funny boundary condition, come back out, and then, roughly speaking, reflect off the centrifugal angular momentum barrier at the outside. And so what you'd get would be a waveform that looks like what we observed, but then followed a fraction of a second later by an echo, which just looks like a copy of the merger and ring down part of the waveform, but let's say with somewhat decreasing amplitude. And then another characteristic reflection time later, you'd see the second bounce of that. So I like the idea a lot. Actually, what I like is the idea that we can maybe test some of the physics near the horizon in this way. It's a great idea. There's a paper that reports actually seeing this in our data, and I don't believe that. A group of people in my group has actually repeated that analysis, and they've actually posted something on the archive about that. But anyway, I think the idea that these observations are going to let us look at the physics of black holes, maybe we'll learn something about what happens near the horizon. It's a great idea.
Other questions? Actually, I have one more technical question. Yeah. In this plot of noise sensitivity, you have many sharp resonances. At least it looks like sharp, undamped mechanical resonances or something like this. Isn't there the danger that a chirp signal, scans over many of them, excites them, and you get some ringing and distortion of the signal?
Yeah, our instruments are, operating. So the question is, what regime are we operating in? We're operating in a very weak signal linear regime. And so as long as the signal, affects the response of the instrument linearly in sort of the low amplitude limit, that's not a problem. Although, it might excite resonances, that's just a linear response and you can just remove it. So I'm not worried about that.
Okay, if there are no further questions, then let's thank Bruce again for the beautiful talk.
Thank you.